Close your eyes and let your mind drift upward into the infinite tapestry of night, where countless points of light whisper ancient secrets across the cosmic dark. Tonight, we embark on a gentle journey through our celestial home, the magnificent spiral of stars we call the Milky Way. Like a luminous river flowing across the heavens, our galaxy cradles us in its vast embrace, holding billions upon billions of suns in a dance that has continued for over 13 billion years. From our small blue world spinning quietly in the cosmic suburbs, we can barely comprehend the true scale of this stellar neighborhood that stretches so far beyond our wildest dreams. As we prepare to explore the breathtaking dimensions of our galactic home, allow your breathing to slow and deepen, matching the ancient rhythm of cosmic time itself. Imagine yourself floating peacefully above Earth's atmosphere, looking out toward that shimmering band of starlight that has guided travelers and inspired wonder for countless generations. We are about to discover just how impossibly vast and beautiful our corner of the universe truly is, measured not in miles or kilometers, but in the gentle currency of light itself, distances so grand that even light, racing at its incredible speed, takes tens of thousands of years to cross from one edge of our galaxy to the other. The Milky Way is far more than just a collection of stars scattered randomly through space. It is an elegant cosmic city with distinct neighborhoods, flowing spiral highways of light, and a mysterious heart that anchors everything in its gravitational embrace. Tonight, as your mind settles into this peaceful exploration, we will wander through stellar nurseries where baby stars are born from cosmic clouds, visit ancient red giants that have watched the universe grow old, and discover how our own sun takes part in an orbital dance so slow and majestic that it completes just one graceful revolution every 225 million years. Before we begin this soothing cosmic voyage, I invite you to visit the Sleepy Cosmoz channel and subscribe to join our growing community of peaceful space explorers. Hit that notification bell so you never miss our gentle journeys through the wonders of the universe, designed to carry you softly toward restful sleep while filling your dreams with the infinite beauty of the cosmos. Like this video, if you're ready to discover just how truly gigantic our Milky Way galaxy is, and let the gentle currents of cosmic wonder wash over you as we drift together through the star-filled immensity of our celestial home. Imagine for a moment that you're holding the most extraordinary map ever created, one that doesn't show streets or cities, but reveals your cosmic address in the vast universe, like a gentle cosmic zoom-out that begins at your fingertips and expands outward through increasingly magnificent scales. We'll discover exactly where Earth sits within the grand architecture of the Milky Way galaxy. This journey will reveal how our seemingly solid world is actually racing through space at incredible speeds, carrying us on a celestial voyage that has been continuing for billions of years without us ever feeling the motion. Let's begin this peaceful exploration right here on Earth, our blue marble spinning quietly in the cosmic void. From space, our planet appears as a delicate jewel suspended in the darkness, wrapped in swirling white clouds and painted with the deep blues of oceans and the warm browns and greens of continents. But Earth is far from stationary. It spins on its axis once every 24 hours, creating our familiar cycle of day and night, while simultaneously orbiting our sun at a distance of approximately 93 million miles, completing this grand circle once every 365 days. This orbital dance places us in what astronomers call the habitable zone, that perfect cosmic sweet spot where liquid water can exist and life can flourish in the gentle warmth of our star. Our solar system itself is like a cosmic family gathered around the warmth of our sun, with 8 planets following their own elegant orbital paths through the darkness. Mercury races closest to our star, completing its year in just 88 Earth days, while distant Neptune takes 165 Earth years to complete a single orbit in the cold outer reaches, where sunlight arrives as barely more than a bright star. Between these extremes, Venus shrouds herself in thick clouds. Mars displays its rusty red surface. Mighty Jupiter reigns as the king of planets with its dozens of moons, and ringed Saturn performs its slow, majestic waltz through space. Our Earth sits in the perfect position, neither too hot nor too cold, in this remarkable planetary orchestra that has been playing its gravitational symphony for over 4.5 billion years. But even our entire solar system, magnificent as it is, represents just the tiniest speck within the vast spiral structure of the Milky Way galaxy. Picture our sun as a single grain of sand on an enormous beach that stretches beyond the horizon. That begins to give you a sense of scale for our cosmic neighborhood. Our solar system is located about 27,000 light-years from the galactic center, positioned on the inner edge of what astronomers call the Orion Arm, also known as the Orion Cygnus Arm. This spiral arm is like a cosmic highway of stars, gas, and dust that winds outward from the galaxy's bright central hub, and we're riding along this stellar expressway at the breathtaking speed of about 515,000 miles per hour as our entire solar system orbits the galactic center. To truly appreciate this cosmic address, imagine that the entire Milky Way galaxy could be shrunk down to the size of the United States. In this scaled-down version, our solar system would be located somewhere around Kansas, definitely not in the crowded downtown area of the galactic center, but not out in the sparse cosmic countryside either. We live in what you might call the galactic suburbs, a region that's peaceful enough to allow stable planetary orbits and the development of life, yet active enough to provide the heavier elements that planets like Earth need to form. This location is particularly special because it places us in the galaxy's habitable zone, where the rate of star formation is steady, dangerous radiation levels are manageable, and the gravitational environment remains stable over the billions of years required for life to evolve and flourish. Our cosmic neighborhood is far from empty, though it might seem that way on a clear night when we look up at the apparently vast spaces between stars. Within just 15 light-years of our Sun, there are approximately 30 other star systems, creating a local stellar community that astronomers sometimes refer to as the solar neighborhood. Our closest stellar neighbors are the 3 stars of the Alpha Centauri system, located about 4.37 light-years away, a distance so vast that if you could somehow travel at the speed of light, it would still take over 4 years to reach them. Among these nearby stars, we find red dwarfs that burn slowly and steadily for hundreds of billions of years, sun-like stars in various stages of their lives, and even some exotic objects like white dwarf stars, the dense, cooling remnants of stars that once shone as brightly as our sun. The story of how we discovered our cosmic address is itself a beautiful tale of human curiosity and scientific detective work spanning centuries. For thousands of years, people looked up at the night sky and naturally assumed that Earth was the center of everything. the fixed point around which the sun, moon, planets, and stars all revolved. This geocentric view seemed perfectly reasonable since we can't feel Earth's motion, and everything in the sky appears to move around us. But gradually, through careful observation and brilliant reasoning, astronomers like Copernicus, Galileo, and Kepler revealed that Earth actually orbits the Sun. Later, in the early 20th century, astronomers made the even more humbling discovery that our Sun is just one ordinary star among hundreds of billions in the Milky Way, and that our galaxy itself is just one of countless others scattered throughout an unimaginably vast universe. This revelation of our true cosmic address, third planet from the Sun, in a solar system located in the Orion arm of the Milky Way galaxy, might initially seem to diminish our importance in the grand scheme of things. But there's something profoundly beautiful and even comforting about understanding our place in this vast cosmic community. We are not isolated or alone, but rather embedded within layers upon layers of cosmic structure, from our local stellar neighborhood to our spiral arm, to our galaxy, to the local group of galaxies beyond. Like nested Russian dolls of increasing scale, each level of cosmic organization reveals new wonders and connections that bind us to the greater universe in ways both physical and spiritual. As you drift towards sleep tonight, carried along by the gentle rhythm of this cosmic explanation, take a moment to feel the amazing reality of your situation. You are riding through space on a planet that spins through day and night while orbiting a star that itself moves through our galaxy at incredible speeds. The atoms in your body were forged in the hearts of ancient stars that lived and died billions of years ago. And the very calcium in your bones and iron in your blood are gifts from cosmic processes that played out across vast stretches of space and time. Your cosmic address places you not at the center of the universe, but at the center of your own unique perspective on infinite wonders, surrounded by the gentle embrace of a galaxy that has been your home since long before Earth even existed. Close your eyes and let your mind drift outward from our solar system's cozy neighborhood, expanding your vision until you can perceive the magnificent architectural masterpiece that is the Milky Way galaxy. Like a cosmic cathedral built from starlight and sculpted by gravity over billions of years, our galaxy displays an elegant design that combines mathematical precision with breathtaking beauty. Tonight, as we explore this celestial architecture together, imagine yourself floating peacefully in the vast darkness of intergalactic space, gazing down upon our galactic home with the wonder of a cosmic architect admiring the greatest construction project in the known universe. The Milky Way belongs to a family of galaxies known as barred spiral galaxies, and understanding this classification helps us appreciate the sophisticated structure that surrounds us. Picture a cosmic pinwheel slowly rotating in the darkness, but instead of simple spokes radiating from the center, imagine graceful spiral arms that curve outward like the most elegant mathematical equations written in stars and stardust. At the heart of this cosmic pinwheel lies a thick rectangular bar of densely packed stars, stretching approximately 27,000 light-years from end to end, a stellar highway that serves as the backbone from which our galaxy's magnificent spiral arms unfurl into the cosmic night. This central bar rotates as a solid unit, much like the spoke of a wheel, and it's this rotation that helps maintain the spiral structure we observe today, acting as a gravitational conductor, orchestrating the grand symphony of stellar motion throughout our galaxy. From the ends of this central stellar bar, two major spiral arms sweep outward in graceful curves that astronomers have named the Scutum Centaurus arm and the Perseus arm. These are not mere collections of randomly scattered stars, but rather organized rivers of stellar light that contain the highest concentrations of both young, brilliant blue stars and ancient, wise red giants that have witnessed the galaxy's long history. Think of these major arms as the galaxy's main boulevards, bustling with stellar activity and glowing with the combined light of hundreds of billions of stars. Each arm maintains its spiral shape through a delicate balance of gravitational forces and orbital mechanics, creating density waves that sweep around the galaxy like slow-motion ocean swells, compressing gas and dust to trigger the birth of new stars in brilliant stellar nurseries that paint the arms in shades of blue and pink. Between these two major spiral arms lie what astronomers call minor arms or spurs, the Sagittarius arm and the Norma arm, which contain fewer stars but serve as important repositories for the galaxy's gas and dust. These secondary features are like the galaxy's residential neighborhoods, quieter than the bustling major arms, but still active with ongoing star formation and stellar evolution. The minor arms bridge the gaps between the major spiral features, creating a more complex and interconnected galactic ecosystem where matter flows in great currents driven by gravitational tides and stellar winds. Within this intricate network of spiral structure, each arm maintains its own character and stellar population, creating a diverse galactic community where different types of stars and stellar systems find their natural homes. Our own solar system resides in a smaller spiral feature called the Orion arm, also known as the Orion spur or the local arm, which extends like a cosmic bridge between the major Perseus and Sagittarius arms. For decades, astronomers considered our local spiral feature to be merely a minor spur, but recent observations have revealed that the Orion arm is actually more substantial and extensive than previously thought, stretching for at least 10,000 light-years and containing enough stars and stellar formation regions to qualify as a significant galactic feature in its own right. This discovery has elevated our cosmic neighborhood from a minor galactic backwater to an important part of the Milky Way's spiral architecture, suggesting that we live in a more dynamic and significant region of the galaxy than our ancestors could have imagined. The spiral arms of the Milky Way are not permanent fixtures carved in cosmic stone, but rather dynamic patterns that flow and evolve like waves in an ocean of stars. These density waves travel around the galaxy at a different speed than the stars themselves, creating a cosmic traffic pattern where stars periodically enter and exit the spiral arms during their orbital journeys around the galactic center. When a star enters a spiral arm, it encounters higher concentrations of gas and dust, increased gravitational influences from neighboring stars, and enhanced magnetic fields that can trigger various stellar processes. Young, massive stars are born preferentially within these dense spiral arms, where abundant raw materials and gravitational compression create ideal conditions for stellar nurseries, while older stars, like our Sun, spend most of their lives in the quieter spaces between the arms, occasionally passing through these stellar highways during their long galactic orbits. The mathematical elegance of spiral structure emerges from the interplay between differential rotation and density wave theory, concepts that reveal the sophisticated physics underlying our galaxy's beautiful architecture. Differential rotation means that stars closer to the galactic center complete their orbits faster than those farther out, much like the inner planets in our solar system orbit the Sun more quickly than the outer ones. This varying orbital speed would normally wind spiral arms tighter and tighter until they disappeared entirely, but the galaxy maintains its spiral structure through density waves, gravitational disturbances that propagate through the galactic disk like ripples on a cosmic pond. These waves compress the interstellar medium as they pass, triggering star formation and creating the bright, well-defined spiral arms we observe, while the underlying stellar population remains distributed more smoothly throughout the galactic disk. The pitch angle of our galaxy's spiral arms, the angle at which they curve outward from the central bar, measures approximately 12 degrees, creating what astronomers classify as a relatively tightly wound spiral pattern. This geometric precision reflects the careful balance between the galaxy's rotation rate, the strength of its central bar, and the properties of its dark matter halo, all working together to maintain stable spiral structure over cosmic time. The arms themselves are estimated to be about 800 parsecs wide, roughly 2,600 light years, creating broad stellar highways that guide the flow of gas, dust, and stars through the galactic disk. Within these spiral features, the concentration of bright, young stars can be 30 to 50% higher than the galactic average, creating the enhanced brightness that makes spiral arms visible across the vast distances of intergalactic space. Recent advances in astronomical observation, particularly using infrared light that can penetrate the dust clouds that obscure our view of the galaxy, have revolutionized our understanding of the Milky Way's architecture. The Spitzer Space Telescope and other infrared observatories have mapped the distribution of stars throughout our galaxy, revealing details of spiral structure that were previously hidden from optical telescopes. These observations confirmed that our galaxy possesses a strong central bar and clarified the relationship between the major and minor spiral arms, showing that the Milky Way's architecture is both more organized and more complex than astronomers had previously realized. The infrared view also revealed additional structural features, including a mysterious arm segment called the far 3 kiloparsec arm that lies along the galaxy's central bar, adding yet another layer to our understanding of galactic architecture. As you allow sleep to gently embrace your consciousness, tonight, let your mind wander through this magnificent spiral architecture that has been your cosmic home for your entire existence. The Milky Way's elegant design represents the perfect marriage of physics and artistry, where gravitational forces and stellar evolution have collaborated over billions of years to create a structure of mathematical beauty and astronomical wonder. Every star you see in the night sky, every constellation that has guided human navigation and imagination, exists within this carefully orchestrated spiral symphony that rotates slowly and majestically through the darkness of space. The galaxy's architecture provides not just a cosmic address for our solar system, but a dynamic, ever-evolving stellar ecosystem that continues to birth new stars, sculpt planetary systems, and create the conditions necessary for worlds like Earth to exist and thrive in the vast cosmos. Let your mind drift now into the most profound contemplation of cosmic abundance, as we explore the breathtaking reality that our Milky Way galaxy contains not merely millions, not billions, but somewhere between 200 and 400 billion individual stars, each one a sun in its own right, many hosting their own families of planets, moons, asteroids, and comets. This astronomical number represents such an overwhelming abundance of stellar light that human language struggles to convey its true magnitude. Yet tonight, we'll journey together through gentle analogies and peaceful imagery to help your mind grasp this cosmic river of stars that flows in majestic currents throughout our galactic home. As you settle into deeper relaxation, imagine each star as a single point of light in an ocean of darkness so vast that light itself requires 100,000 years to travel from one edge of our galaxy to the other, carrying with it the ancient stories of stellar birth, life, and transformation. To truly appreciate the stellar population of the Milky Way, we must first abandon our earthbound perspective and embrace the reality that what we see in our night sky represents only the tiniest fraction of our galaxy's stellar residents. On the clearest, darkest night, far from the glow of city lights, the human eye can perceive approximately 6,000 stars scattered across the celestial sphere. A number that seems impressive until we realize it represents less than 100 millionth of 1% of the stars that actually exist in our galaxy. The vast majority of the Milky Way's stellar citizens remain invisible to our naked eyes, hidden by the sheer scale of galactic distances, the absorption of interstellar dust, and the limitations of human vision. Even our most powerful ground-based telescopes have cataloged only a small percentage of the galaxy's total stellar inventory, leaving billions upon billions of stars to shine unseen and unexplored in the cosmic depths beyond our current observational reach. The stars of the Milky Way exist in a staggering diversity of types, sizes, colors, and ages, creating a cosmic ecosystem of remarkable complexity and beauty. At one end of the stellar spectrum, we find the massive blue supergiant stars, stellar titans that can measure more than 40 times the mass of our Sun and shine with the luminosity of millions of solar luminosities. These brilliant blue-white stars burn their nuclear fuel at such prodigious rates that they live fast and die young, consuming their entire hydrogen reserves in just a few million years before exploding as spectacular supernovae that briefly outshine entire galaxies. At the opposite extreme, we encounter the red dwarf stars, small, cool, long-lived stellar citizens that represent the most numerous type of star in our galaxy, accounting for roughly 75% of all stellar residents. These modest red stars burn their nuclear fuel so efficiently and conservatively that they can continue shining steadily for hundreds of billions of years, far longer than the current age of the universe itself. Between these extremes lies our own Sun, a middle-aged, middle-mass star that astronomers classify as a G-type main sequence star, neither the largest nor the smallest, neither the hottest nor the coolest, but rather a perfectly ordinary stellar citizen that represents the cosmic sweet spot where nuclear fusion can proceed steadily for about 10 billion years. Our Sun has been burning hydrogen in its core for approximately 4.6 billion years, and will continue this stellar alchemy for another 5 billion years, providing stable energy output that allows complex chemistry and biological evolution to unfold on planets like Earth. Throughout the Milky Way, millions of similar Sun-like stars pursue their own nuclear careers, and recent astronomical surveys suggest that a significant percentage of these stellar cousins host their own planetary systems, many of which may harbor the conditions necessary for liquid water and potentially even life itself. The spatial distribution of these hundreds of billions of stars throughout the Milky Way follows patterns that reflect both the galaxy's formation history and its ongoing evolution. The central bulge region, concentrated within about 10,000 light-years of the galactic center, contains roughly 20 billion stars packed into a relatively compact, spherical volume, creating a stellar density thousands of times higher than in our local solar neighborhood. These central stars are predominantly older, redder stellar populations that formed during the galaxy's earliest epochs, when the interstellar medium was less enriched with the heavy elements produced by previous generations of stellar evolution. Moving outward from this central concentration, the galactic disk contains the majority of the Milky Way's stellar population, with star density decreasing exponentially as we move toward the galaxy's outer edges. The disk itself shows a complex vertical structure, with younger stars concentrated in a thin disk layer only about 1,000 light-years thick, while older disk stars occupy a thicker distribution that extends several thousand light-years above and below the galactic plane. Within the galactic disk, the spiral arms represent regions of enhanced stellar density and ongoing star formation, creating rivers of starlight that flow in graceful curves throughout the galaxy. These spiral features contain approximately 10 to 30% more stars than the spaces between the arms, with the enhancement being particularly pronounced for young, hot, blue stars that are born preferentially within the dense molecular clouds found along the spiral arms. As you drift deeper into peaceful contemplation, imagine these spiral arms as cosmic highways where stellar traffic flows in organized patterns, with older stars like our Sun occasionally passing through these busier regions during their long orbital journeys around the galactic center. The spiral arms also serve as galleries for stellar art, showcasing brilliant stellar nurseries, colorful nebulae, and the dramatic explosions of supernovae that enrich the interstellar medium with the heavy elements necessary for planet formation and potentially the emergence of life. The outer regions of the Milky Way, beyond the visible edge of the galactic disk, contain additional stellar populations that extend the galaxy's boundaries far beyond what we observe in optical light. The stellar halo, a roughly spherical distribution of ancient stars that surrounds the entire galactic disk, may contain several billion stars scattered throughout a volume that extends at least 100,000 light-years from the galactic center. These halo stars are among the oldest objects in the galaxy, with ages approaching 13 billion years, making them contemporary with the galaxy's initial formation. Many halo stars belong to globular clusters, dense, spherical aggregations containing hundreds of thousands of stars packed into regions only a few dozen light-years across. These globular clusters serve as stellar time capsules, preserving pristine examples of the galaxy's earliest stellar generations and providing crucial insights into the chemical and physical conditions that prevailed during the Milky Way's youth. Recent advances in astronomical observation have revolutionized our understanding of stellar populations throughout the Milky Way, revealing that the galaxy's stellar census is even more complex and interesting than previously imagined. The European Space Agency's Gaia mission has measured precise positions, distances, and motions for over 1 billion stars within our galaxy, creating the most detailed three-dimensional map of stellar distribution ever assembled. These observations have revealed previously unknown stellar streams, rivers of stars that were disrupted from smaller satellite galaxies that fell into the Milky Way's gravitational embrace billions of years ago. The Gaia data has also identified co-moving groups of stars that were born together in the same stellar nurseries, but have since dispersed throughout the galaxy, allowing astronomers to trace the history of star formation and galactic evolution with unprecedented precision. The chemical composition of stars throughout the Milky Way tells the story of cosmic evolution written in stellar atmospheres, revealing how the galaxy has gradually enriched itself with heavy elements over billions of years of stellar evolution. The oldest stars in the galactic halo contain almost no elements heavier than hydrogen and helium, reflecting their birth from the primordial material left over from the Big Bang. In contrast, younger stars like our Sun show substantial abundances of carbon, oxygen, silicon, iron, and other heavy elements that were forged in the nuclear furnaces of previous stellar generations and distributed throughout the galaxy by stellar winds and supernova explosions. This progressive chemical enrichment has been essential for the formation of rocky planets, complex molecules, and ultimately the emergence of life, making the stellar population of the Milky Way not just a collection of individual light sources, but rather a vast chemical processing plant that has been manufacturing the building blocks of complexity for over 13 billion years. As sleep gently embraces your consciousness tonight, let your imagination soar among this incredible river of stars that surrounds and encompasses your existence. Every breath you take contains oxygen atoms forged in the cores of massive stars that lived and died billions of years ago, contributing their nuclear ashes to the cosmic recycling process that eventually led to the formation of our solar system and planet Earth. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were manufactured in stellar furnaces and scattered through the galaxy by stellar explosions, connecting you intimately to this vast stellar community that spans hundreds of thousands of light years. In the peaceful darkness behind your closed eyelids, you can almost sense the gentle gravitational influence of those hundreds of billions of stellar neighbors, each following its own orbital path through the galaxy, each contributing to the grand cosmic dance that has been continuing since long before Earth existed and will continue long after our planet has returned to stardust. Allow your consciousness to expand now into the vast, flattened expanse that forms the primary structure of our Milky Way galaxy. The magnificent galactic disk that stretches an incredible 100,000 light years from edge to edge while maintaining a remarkably thin profile of only about 1,000 light years in thickness. Imagine this cosmic structure as a vast celestial pizza or pancake, so perfectly proportioned that if you were to scale it down to the size of a dinner plate, it would be thinner than a human hair. Yet within this gossamer thin disk lies the overwhelming majority of our galaxy's visible matter. Stellar population and ongoing cosmic activity. Tonight, as we journey together through this peaceful exploration of galactic architecture, let your mind drift gently through this disk-like realm that has served as humanity's cosmic neighborhood for our entire existence, containing not only our solar system, but also the spiral arms, stellar nurseries, and cosmic phenomena that make our galaxy one of the most beautiful and dynamic structures in the known universe. The galactic disk represents one of the most remarkable examples of cosmic organization and gravitational architecture in the universe, demonstrating how billions of years of rotation and gravitational settling have created a structure of almost mathematical perfection. This disk formed through a process that astronomers call gravitational collapse and angular momentum conservation, a cosmic dance in which the original, roughly spherical cloud of gas and dark matter that would become our galaxy gradually flattened as it rotated, much like a spinning ball of pizza dough stretches into a flat, circular shape under the influence of centrifugal force. The disk reaches its maximum density along the galactic plane, the central plane of rotation that serves as the galaxy's equator, with stellar density dropping off exponentially as we move vertically away from this plane in either direction. Our solar system sits remarkably close to this galactic plane, only about 95 light-years above it, placing us in the thick of the galactic action and providing us with an edge-on view of the disk that creates the luminous band we call the Milky Way, stretching across our night sky. Within this vast galactic disk, astronomers have identified two distinct structural components that reflect different epochs of galactic evolution and stellar formation. The thin disk, which extends only about 700 light-years above and below the galactic plane, contains the youngest stellar populations, the most active star-forming regions, and the highest concentrations of gas and dust that serve as raw materials for ongoing cosmic construction projects. This thin disk represents the galaxy's most recent and ongoing chapter of stellar birth, containing stars with ages ranging from just a few million years to about 10 billion years, including our own middle-aged sun. In contrast, the thick disk extends several thousand light-years vertically from the galactic plane and contains older stellar populations that formed during the galaxy's earlier, more turbulent epochs, when stellar formation rates were higher and supernova explosions more frequent. These older thick disk stars preserve chemical signatures from the galaxy's youth, when the interstellar medium contained lower abundances of heavy elements and stellar formation proceeded under different physical conditions than we observe today. The rotation of the galactic disk creates one of the most mesmerizing aspects of our galaxy's behavior: differential rotation that varies smoothly from the inner regions to the outer edges in a pattern that reflects the complex interplay between the galaxy's mass distribution and gravitational dynamics. Near the galactic center, within about 3,000 light-years of Sagittarius A star, the rotation curve shows solid body rotation, meaning that stars and gas clouds orbit like points on a spinning rigid disk, with orbital velocities that increase linearly with distance from the center. Beyond this central region, however, the galaxy displays what astronomers call Keplerian rotation, similar to the motion of planets around the Sun, where more distant objects move more slowly in their orbits. Yet in the galaxy's outer regions, something remarkable occurs. The rotation curve flattens out, meaning that stars at the galaxy's edge move nearly as fast as those in the inner regions, a phenomenon that provides some of the strongest evidence for the existence of dark matter halos that extend far beyond the visible boundaries of galactic disks. Throughout the galactic disk, the distribution of different stellar populations creates a cosmic ecosystem of remarkable diversity and beauty. The youngest and most massive stars, brilliant blue and white giants that burn their nuclear fuel at prodigious rates, concentrate primarily along the spiral arms, where ongoing star formation creates stellar nurseries filled with glowing hydrogen gas, colorful nebulae, and newly formed star clusters. These stellar nurseries represent some of the most active and dynamic regions in the galaxy, where dense molecular clouds collapse under their own gravity to birth new generations of stars, planets, and potentially the seeds of future life. The most massive of these young stars live fast and die spectacularly, exploding as supernovae that enrich the interstellar medium with heavy elements, while also triggering shock waves that can compress nearby gas clouds and trigger additional episodes of star formation, creating a feedback cycle that has been sculpting the galactic disk for billions of years. As we move away from the active star-forming regions along the spiral arms, we encounter the more sedate regions between the arms, where older stellar populations dominate the local stellar census. These inter-arm regions contain stars like our Sun, middle-aged, stable, long-lived stellar citizens that formed from previous generations of stellar recycling and now pursue quiet orbits around the galactic center. The spaces between spiral arms provide more stable, less turbulent environments where planetary systems can form and evolve over the billions of years required for complex chemistry and potentially biology to develop. It is no coincidence that our solar system currently resides in such a relatively quiet interarm region, as the more active spiral arms, with their frequent supernova explosions and intense stellar radiation, would pose significant challenges for the long-term stability required for life to emerge and flourish on planets like Earth. The chemical composition of the galactic disk reveals the ongoing story of cosmic evolution written in stellar atmospheres and interstellar gas clouds throughout this vast structure. The disk shows a clear metallicity gradient, with stars closer to the galactic center generally containing higher abundances of elements heavier than hydrogen and helium, while stars in the outer regions of the disk show lower heavy element abundances. This gradient reflects the inside-out formation of the galactic disk, where star formation began earliest and proceeded most vigorously in the central regions before gradually spreading outward to the galaxy's edges. The spiral arms serve as highways for chemical mixing, transporting gas enriched with heavy elements from inner regions toward the outer disk, while also facilitating the inward flow of relatively pristine gas from the galaxy's outer edges and halo regions. The vertical structure of the galactic disk provides insights into the galaxy's formation history and the various physical processes that have shaped its evolution over cosmic time. The scale height of the disk, the distance above or below the galactic plane where stellar density drops to a certain fraction of its midplane value, varies for different stellar populations, with younger stars showing smaller scale heights and older stars showing progressively larger scale heights. This age-velocity dispersion relationship reflects the gradual heating of stellar orbits over time through gravitational encounters with molecular clouds, spiral density waves, and other disk structures. The thickening of stellar orbits with age creates the thick disk component and provides a fossil record of the galaxy's dynamical evolution, allowing astronomers to reconstruct the galaxy's history by studying the kinematics and chemical compositions of stars at different heights above the galactic plane. Recent observations have revealed that the galactic disk is far from a perfect, flat structure, instead showing various warps, flares, and asymmetries that reflect the complex gravitational influences of satellite galaxies, dark matter substructures, and the galaxy's ongoing interaction with its cosmic environment. The outer regions of the disk show a distinct warp, where the disk plane tilts upward on one side of the galaxy and downward on the opposite side, creating a subtle but measurable S-shaped curve when viewed edge-on. This warping likely results from gravitational torques exerted by the large and small Magellanic clouds our galaxy's most prominent satellite companions, whose gravitational influence creates tidal forces that distort the outer disk's shape. Additional asymmetries in the disk structure may result from ancient collisions with smaller galaxies that have since been absorbed into the Milky Way's structure, leaving behind subtle gravitational scars that continue to influence the galaxy's morphology billions of years after the original interactions occurred. As you allow peaceful sleep to embrace your consciousness tonight, imagine yourself floating gently through this vast galactic disk that has been your cosmic home for your entire existence. The disk contains not only the matter from which planets and life emerged, but also the ongoing stellar processes that continue to create the heavy elements necessary for complex chemistry and biology. Every atom in your body, except hydrogen, was manufactured in the nuclear furnaces of stars within this disk, distributed through the galactic ecosystem by stellar winds and supernova explosions, and eventually incorporated into the molecular clouds from which our solar system formed 4.6 billion years ago. The thin disk that seems so vast and empty between the stars actually teems with invisible activity, magnetic fields threading through space, cosmic rays accelerated by stellar explosions, and the subtle gravitational interactions that maintain the galaxy's graceful spiral structure across billions of years of cosmic evolution. Let your mind now expand into the gentle contemplation of one of the most beautiful and profound cosmic phenomena, the elegant orbital dance that our entire solar system performs as it travels through the Milky Way galaxy. Picture our familiar family of planets, moons, asteroids, and comets not as a stationary collection of celestial objects, but as a unified cosmic ballet troupe that moves together through space at breathtaking speeds, following a graceful elliptical path around the galactic center that takes approximately 225 to 250 million years to complete just once. This galactic year, the time required for our solar system to make a single orbit around the galaxy, represents a temporal scale so vast that dinosaurs roamed Earth during our last position in this same cosmic location. And by the time we return to this point in space again, our planet and solar system will have undergone transformations we can barely imagine. Our solar system currently resides approximately 27,000 light-years from the galactic center, positioned on the inner edge of the Orion Arm, in what astronomers consider the galactic suburbs, neither too close to the crowded and radiation-intensive central regions, nor too far out in the sparse and relatively inactive outer reaches of the galactic disk. This location places us roughly halfway between the galaxy's center and its visible edge, in a region where star formation proceeds at a moderate pace. Supernova explosions occur infrequently enough to avoid sterilizing planetary surfaces, and the gravitational environment remains stable enough to allow planetary orbits to persist for billions of years. From our perspective within the galactic disk, we observe the rest of our galaxy edge on, which creates the appearance of that luminous band of starlight stretching across our night sky that we call the Milky Way. A view that would be impossible if we lived in the galaxy's central bulge, or outer halo regions. The orbital motion of our solar system around the galactic center occurs at the remarkable velocity of approximately 220 to 230 kilometers per second, which translates to roughly 490,000 to 515,000 miles per hour. A speed so incredible that we could travel from Earth to the Moon in less than an hour if we could somehow harness this galactic orbital velocity for interplanetary travel. Yet despite this tremendous speed, we remain completely unaware of our cosmic journey because everything in our local stellar neighborhood moves together through space, creating a reference frame in which the nearby stars appear relatively stationary from our perspective. This galactic orbital motion differs fundamentally from the chaotic random motions we might expect. Instead, it follows the ordered rotation of the galactic disk, with our solar system bobbing gently up and down relative to the galactic plane approximately every 33 million years, while simultaneously pursuing its grand circular journey around the galaxy's center. During our solar system's stately progress around the galaxy, we periodically encounter different galactic environments that may influence conditions on Earth and throughout our planetary system. As we orbit the galactic center, we occasionally pass through the galaxy's spiral arms, regions of higher stellar density, active star formation, and increased cosmic ray flux that could potentially affect Earth's climate, atmospheric chemistry, and even biological evolution. Some scientists have hypothesized that these periodic passages through spiral arms might correlate with mass extinction events in Earth's fossil record, though this connection remains a subject of active scientific investigation and debate. The spiral arm passages occur roughly every 100 to 150 million years, meaning that since complex life emerged on Earth, our planet has experienced several complete transits through these cosmic highways of enhanced stellar activity. The path of our solar system through the galaxy is not a perfect circle, but rather follows a slightly elliptical orbit that brings us closer to and farther from the galactic center over the course of each 225 million year galactic year. Currently, we appear to be near the outer extent of our elliptical orbit, but the exact eccentricity and orientation of our galactic orbit remain subjects of ongoing astronomical research. The solar system's orbital motion also includes a vertical component relative to the galactic plane, causing us to oscillate above and below the galaxy's central disk with a period of approximately 64 million years. This vertical oscillation carries us as much as 230 light-years above or below the galactic plane, creating variations in our exposure to cosmic radiation from the galaxy's central regions and potentially influencing the rate at which high-energy particles reach Earth's atmosphere. The gravitational forces that govern our solar system's galactic orbit arise from the combined mass of all the matter within our orbital radius, not just the visible stars and gas clouds, but also the vast quantities of dark matter that permeate the galaxy's halo. The rotation curve of the Milky Way, which describes how orbital velocities vary with distance from the galactic center, provides strong evidence for the existence of this dark matter component, which outweighs the visible matter by a factor of at least 5 to 1. Our solar system's orbital velocity remains remarkably constant over cosmic timescales because we exist within what astronomers call the flat portion of the galactic rotation curve, where the gravitational effects of dark matter maintain nearly uniform orbital speeds across a wide range of galactic radii. This stability in our galactic orbit has been crucial for the long-term habitability of Earth, as dramatic changes in orbital velocity could expose our planet to dangerous levels of cosmic radiation or gravitational perturbations that might destabilize planetary orbits. The concept of our solar system's galactic motion helps place human history and even geological timescales into cosmic perspective. Since anatomically modern humans first appeared roughly 200,000 years ago, our solar system has traveled approximately 200 light-years along its galactic orbit, a distance that encompasses thousands of nearby star systems, but represents less than 1/10 of 1% of a complete galactic revolution. Even the entire history of life on Earth, spanning roughly 3.8 billion years, encompasses only about 17 complete galactic orbits, meaning that our planet has returned to approximately the same galactic location fewer than 20 times since the first primitive organisms emerged in ancient oceans. This cosmic perspective reveals that while Earth's biological evolution has proceeded through countless cycles of extinction and diversification, our planet's galactic environment has changed relatively slowly, providing a stable cosmic backdrop against which terrestrial evolution could unfold over billions of years. The gravitational environment through which our solar system travels includes not only the smooth background of galactic mass, but also the more localized gravitational influences of nearby stars, molecular clouds, and other celestial objects that we encountered during our galactic journey. Over the course of millions of years, these gravitational perturbations can slightly alter the orbits of objects in the outer reaches of our solar system, particularly in the Oort cloud, the spherical shell of icy comets that extends roughly halfway to the nearest star. Occasionally, these gravitational influences can redirect Oort cloud objects toward the inner solar system, creating the spectacular comets that have fascinated humans throughout recorded history. Some astronomers have suggested that our solar system's passage through dense molecular cloud regions might increase the frequency of comet impacts on Earth, potentially contributing to periodic climate changes or even mass extinction events, though the evidence for such correlations remains inconclusive. The discovery of our solar system's galactic motion represents one of the great intellectual achievements of modern astronomy, fundamentally changing our understanding of Earth's place in the cosmic hierarchy. For most of human history, people naturally assumed that Earth was stationary at the center of the universe, with all celestial objects revolving around our planet. Even after astronomers recognized that Earth orbits the Sun, it took centuries to realize that our entire solar system participates in the grand rotation of the galaxy. This revelation places our cosmic address in a dynamic rather than static context, revealing that we are not permanent residents of any particular region of space, but rather cosmic travelers on an eternal journey through the galaxy's vast territories. The knowledge that we are all passengers aboard Spaceship Earth as it sails through the galaxy at 500,000 miles per hour adds a profound dimension to our understanding of human existence and our relationship to the cosmos. As you drift toward peaceful sleep tonight, carried by the gentle rhythm of this cosmic explanation, take comfort in the knowledge that you are participating in one of the universe's most elegant dances. While you rest, Earth continues its familiar rotation, creating the cycle of day and night that has governed life on our planet for billions of years. Simultaneously, our planet pursues its annual orbit around the Sun, creating the seasons that bring variety and renewal to terrestrial ecosystems. And at the grandest scale, our entire solar system glides silently through the galaxy at tremendous speed, following an orbital path that connects us to the cosmic community of hundreds of billions of stars. This nested hierarchy of motions, rotation, revolution, and galactic orbit creates the stable yet dynamic environment that has allowed complex chemistry, geological processes, and ultimately life itself to emerge and flourish in our corner of the Milky Way galaxy. Allow your consciousness to drift gently outward from our solar system into the vast stellar neighborhoods that surround us, where cosmic distances are measured not in millions of miles, but in trillions upon trillions, creating spaces so immense that light itself, traveling at 186,000 miles per second, requires years to bridge the gaps between stellar neighbors. In this peaceful exploration of our galactic community, we discover that even the seemingly empty darkness between stars contains wonders beyond imagination, populated by stellar companions whose stories intertwine with our own across the cosmic eons. Tonight, as we journey together through these neighborhoods of space, let your mind expand to embrace the magnificent scale of stellar distances while finding comfort in the knowledge that we are not alone in the cosmic dark, but rather part of an extended stellar family that spans thousands of light years in every direction. Our nearest stellar neighbor, the Alpha Centauri system, lies a mere 4.37 light years away, a distance that may sound small in astronomical terms, but represents a journey that would take our fastest spacecraft tens of thousands of years to complete. This remarkable triple star system consists of Alpha Centauri A and B, two sun-like stars locked in a cosmic dance around their common center of mass, accompanied by the small red dwarf Proxima Centauri, which holds the distinction of being the closest individual star to our solar system. Proxima Centauri, despite its proximity, shines so dimly that it cannot be seen with the naked eye from Earth, reminding us that stellar brightness depends not only on distance, but also on the intrinsic luminosity of the star itself. This humble red dwarf, with only about 12% of our Sun's mass, burns its nuclear fuel so efficiently that it will continue shining for hundreds of billions of years, long after our Sun has exhausted its hydrogen and evolved into a white dwarf star. Beyond Alpha Centauri, our local stellar neighborhood extends outward in all directions, like a three-dimensional web of light points scattered through the cosmic dark. Within a sphere of just 12 light-years radius centered on our Sun, astronomers have cataloged approximately 33 known stellar systems, creating a relatively sparse cosmic community where the average distance between neighbors measures several light-years. These nearby stars represent a diverse stellar population that includes red dwarfs like Proxima Centauri, sun-like yellow stars such as Alpha Centauri A, orange dwarf stars, and even some white dwarf remnants, the cooling embers of stars that completed their nuclear evolution billions of years ago. Each of these stellar neighbors follows its own orbital path around the galactic center, creating a slowly changing pattern of stellar positions that astronomers call proper motion, a dance so gradual that the constellations we see today will require tens of thousands of years to show noticeable changes to future human observers. The famous star Sirius, the brightest star in our night sky, lies approximately 8.6 light-years away and serves as a perfect example of how stellar properties can differ dramatically from our Sun despite relatively close cosmic proximity. Sirius A shines with more than 20 times our Sun's luminosity, making it visible even in daylight under certain conditions, while its white dwarf companion, Sirius B, represents the dense remnant of a star that once outshone its current primary companion. This binary system illustrates the complex stellar evolution that occurs throughout our galactic neighborhood, where stars of different masses age at different rates, creating stellar pairs with dramatically different evolutionary histories. The gravitational dance between Sirius A and B takes approximately 50 years to complete, demonstrating how gravity continues to choreograph celestial motions across vast distances and timescales that dwarf human experience. Another fascinating neighbor, Barnard's Star, located about 6 light-years away, holds the record for the largest proper motion of any known star, racing across the sky at such a rapid pace that it will noticeably change position relative to background stars within a human lifetime. This red dwarf star is approaching our solar system and will reach its closest point of approximately 3.8 light-years in about 9,800 years before beginning to recede again into the cosmic distance. Barnard's Star reminds us that our stellar neighborhood exists in constant, slow motion, with stellar positions shifting gradually over time as each star follows its own unique orbital path around the galactic center. The star's high proper motion results from a combination of its relatively close distance and its orbital velocity, which carries it through space at about 140 kilometers per second relative to our Sun. The red dwarf Wolf 359, lying approximately 7.9 light-years from Earth, represents one of the intrinsically faintest stars in our cosmic neighborhood, shining with only about 1/10,000th of our Sun's luminosity. Despite its proximity, Wolf 359 requires a telescope to observe from Earth, illustrating how the vast majority of stars in our galaxy remain invisible to naked eye observation due to their low intrinsic brightness. This small star, with only about 16% of our Sun's mass, exemplifies the most common type of star in the Milky Way galaxy, suggesting that red dwarfs may host a significant fraction of the galaxy's potential planetary systems and possibly even habitable worlds. The longevity of red dwarf stars, they can burn steadily for hundreds of billions of years, makes them attractive targets in the search for long-term planetary stability and the potential development of complex life over cosmic timescales. Within our extended stellar neighborhood, spanning roughly 25 light-years from the Sun, we encounter several stellar systems that have captured human imagination and scientific interest. The star Vega, located about 25 light-years away in the constellation Lyra, served as the northern pole star around 12,000 years ago, and will hold that position again in approximately 13,727 CE, demonstrating how the slow precession of Earth's rotational axis creates long-term changes in our planet's relationship to the stellar backdrop. Vega also holds historical significance as the first star ever photographed and the first to have its spectrum recorded, making it a cornerstone in the development of stellar astronomy. This brilliant blue-white star, with about twice our Sun's mass, represents a different stellar type from our Sun, and will evolve much more rapidly, exhausting its nuclear fuel in less than 1 billion years compared to our Sun's 10 billion-year lifespan. The multiple star system of Epsilon Eridani, situated approximately 10.5 light-years away, resembles a younger version of our solar system and has become a favorite target for astronomers studying planetary formation and evolution. This orange dwarf star, slightly smaller and cooler than our Sun, but with a similar stellar type, appears to host at least one confirmed planet and possibly additional planetary companions, making it one of the closest known planetary systems to Earth. The star's youth, estimated at only about 400 to 800 million years old compared to our Sun's 4.6 billion years, provides insights into how stellar and planetary systems evolve over cosmic time. Observations of Epsilon Eridani have revealed debris disks of dust and rocky material that may represent the early stages of planet formation, offering a window into the processes that likely occurred in our own solar system billions of years ago. The discovery of exoplanets around many of our stellar neighbors has revolutionized our understanding of planetary systems and raised tantalizing questions about the potential for life beyond Earth. Proxima Centauri b, orbiting within the habitable zone of our nearest stellar neighbor, represents the closest confirmed exoplanet to Earth and has become a prime target for future interstellar exploration missions. Similarly, several other nearby stars, including Wolf 1061, Gliese 667c, and Kepler 438, host planets that lie within their stars' habitable zones where liquid water could potentially exist on planetary surfaces. These discoveries suggest that planetary systems may be common throughout our galactic neighborhood and possibly throughout the entire Milky Way galaxy, raising the statistical probability that some of these worlds might harbor conditions suitable for life as we know it. The gravitational interactions between our Sun and its stellar neighbors create subtle but measurable effects that astronomers can detect through precise observations. Over time scales of millions of years, these gravitational perturbations can slightly alter the orbits of objects in the outer reaches of our solar system, particularly in the Oort cloud, where comets reside at the very edge of our Sun's gravitational influence. Occasionally, passing stars may deflect Oort cloud objects toward the inner solar system, creating the spectacular long-period comets that grace our skies with their luminous tails. The most famous example of such gravitational influence occurred about 70,000 years ago when the red dwarf star Schultz's star passed within about 1 light year of our solar system, close enough to potentially disturb cometary orbits and send some objects on trajectories toward the inner planets. As you allow peaceful sleep to embrace your consciousness tonight, take comfort in knowing that you exist within a cosmic community of stellar neighbors, each following its own ancient path through the galaxy, while contributing to the gravitational symphony that has shaped our corner of the Milky Way for billions of years. These stellar companions, though separated by distances that challenge human comprehension, remain connected through the invisible threads of gravity and the shared history of galactic evolution. The light from these neighboring stars that reaches your eyes tonight began its journey years ago, carrying with it the photons that were produced in stellar cores through the same nuclear fusion processes that power our Sun. In the gentle darkness behind your closed eyelids, you can almost sense the presence of these distant stellar lighthouses, each one a sun in its own right, possibly warming planets where other forms of consciousness might be gazing back toward our own solar system and wondering about the cosmic community that surrounds us all in the vast, star-filled embrace of the Milky Way galaxy. Let your mind now journey toward the most enigmatic and powerful region of our Milky Way galaxy, the mysterious galactic center, where gravity itself becomes so intense that it warps the very fabric of space and time around a supermassive black hole called Sagittarius A star. This cosmic giant, containing more than 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury, serves as the gravitational anchor that holds our entire galaxy together in its elegant spiral dance. Tonight, as we drift peacefully through this exploration of our galaxy's heart, imagine this central black hole not as a cosmic monster to fear, but as the gentle gravitational conductor of a stellar orchestra containing hundreds of billions of stars, each following its appointed path in the grand symphony of galactic motion that has been playing for over 13 billion years. From our safe distance of 27,000 light years, We can observe and wonder at this cosmic phenomenon while remaining comfortably nestled in the galaxy's suburban regions, where stable planetary orbits allow life to flourish. The supermassive black hole at our galaxy's center represents one of the most extreme environments in the known universe, where the normal laws of physics as we experience them give way to the exotic predictions of Einstein's general relativity. Within the event horizon of Sagittarius, a star, that invisible boundary, approximately 12 million miles in radius, where nothing, not even light, can escape, space and time become so distorted that they lose their familiar meaning. Yet this cosmic giant does not actively consume matter like some cosmic vacuum cleaner. Instead, it influences its surroundings primarily through its immense gravitational field, which extends far beyond the event horizon to shape the orbits of stars, gas clouds, and other celestial objects throughout the central regions of our galaxy. The black hole's gravity creates what astronomers call the central bulge, a roughly spherical region containing approximately 20 billion stars packed into a volume only about 10,000 light-years across, creating stellar densities thousands of times higher than in our local solar neighborhood. Surrounding Sagittarius, a star, astronomers have discovered a fascinating population of stars that orbit the black hole at tremendous velocities, some completing their elliptical paths in periods ranging from just 16 years to several centuries. These stars, designated with names like S0-2, S0-102, and S0-38, provide natural laboratories for testing Einstein's theories under the most extreme gravitational conditions accessible to direct observation. As these stars swing close to the black hole during their closest approaches, they reach speeds of up to 7,650 kilometers per second, more than 2.5% of the speed of light. While experiencing gravitational forces so intense that their orbital motions provide confirmation of relativistic effects such as gravitational redshift and the precession of elliptical orbits, these stellar daredevils somehow survived the violent processes that created the central black hole, perhaps migrating inward from more distant regions of the galaxy, or forming from gas clouds that were compressed by the black hole's gravitational influence. The region surrounding our galaxy's central black hole contains not only these high-velocity stars, but also vast quantities of hot, ionized gas that glow with X-ray and radio emissions detectable by Earth-based telescopes. This material forms what astronomers call an accretion disk, though in the case of Sagittarius A star, the disk appears to be relatively sparse and low density compared to the more active black holes found in other galaxies. The intermittent feeding of material into the black hole creates occasional flares of high-energy radiation that can be observed by space-based X-ray telescopes, providing insights into the physical processes occurring near the event horizon. These observations suggest that our galaxy's central black hole is currently in a relatively quiet phase, consuming material at a slow rate compared to its maximum possible appetite, which helps explain why the galactic center is not blazing with the intense radiation that characterizes more active galactic nuclei in other parts of the universe. The discovery and characterization of Sagittarius A star represents one of the greatest triumphs of modern astronomy, requiring decades of patient observation and technological advancement to peer through the thick clouds of interstellar dust that obscure our view of the galactic center. Using infrared and radio telescopes that can penetrate this cosmic fog, astronomers have mapped the motions of stars near the galactic center with extraordinary precision, tracking their positions over many years to reveal the orbital patterns that betrayed the presence of an invisible massive object at the galaxy's heart. The 2020 Nobel Prize in Physics was awarded to researchers who made fundamental contributions to this discovery, recognizing the profound importance of understanding the role that supermassive black holes play in galactic structure and evolution. The Event Horizon Telescope collaboration subsequently produced the first direct image of Sagittarius A star in 2022, capturing the shadow cast by the black hole against the glowing material in its immediate vicinity. The formation and evolution of supermassive black holes like Sagittarius A star remain among the most fascinating unsolved puzzles in astrophysics, with several competing theories attempting to explain how these cosmic giants grew to such enormous masses in the relatively short time since galaxy formation began. One possibility suggests that these black holes formed from the collapse of the first generation of massive stars in the early universe, then grew by accreting material over billions of years of galactic evolution. Alternative theories propose that supermassive black holes might have formed more directly from the collapse of massive gas clouds during the early epochs of galaxy formation, bypassing the stellar formation phase entirely. Regardless of their origin, these central black holes appear to play crucial roles in regulating star formation throughout their host galaxies, creating feedback mechanisms that influence the distribution of gas and dust across galactic scales, and possibly determining the ultimate size and structure of mature spiral galaxies like our Milky Way. The gravitational influence of Sagittarius A star extends far beyond its immediate neighborhood, contributing to the overall rotation curve of our galaxy and helping to maintain the organized motions that characterize the galactic disk. The combined gravitational effects of the central black hole, the surrounding bulge of stars, and the galaxy's dark matter halo create the mass distribution that determines orbital velocities throughout the galaxy, including the 220 km per second orbital speed of our own solar system. Computer simulations of galaxy formation suggest that the growth of central supermassive black holes is intimately connected to the assembly of their host galaxies, with the black hole mass correlating strongly with properties of the galactic bulge, indicating a fundamental relationship between the smallest and largest scales of galactic structure. This connection implies that understanding supermassive black holes is essential for comprehending how galaxies like our Milky Way formed and evolved over cosmic time. The environment near the galactic center also hosts some of the most extreme stellar populations in the galaxy, including stars that are among the most massive, luminous, and short-lived known to exist anywhere in the Milky Way. These stellar giants, with masses exceeding 100 times that of our Sun, burn their nuclear fuel at such prodigious rates that they complete their entire life cycles in just a few million years, ending their brief but brilliant lives in spectacular supernova explosions that enrich the surrounding interstellar medium with heavy elements. The formation of such massive stars near the galactic center may be facilitated by the high-density environment and the gravitational influence of the central black hole, which can compress gas clouds to densities that favor the formation of very massive stellar objects. These stars also contribute to the high-energy environment near the galactic center, producing intense stellar winds, ultraviolet radiation, and eventually supernova explosions that heat the surrounding gas and create the complex structures observed in radio and X-ray images of the galactic center region. Recent observations have revealed that the galactic center region contains not just isolated stars and gas clouds, but also complex structures such as vast filamentary features that may represent the remnants of ancient star formation events, or the signatures of magnetic field interactions with the central black hole. These features, visible in radio wavelength observations, extend hundreds of light years outward from the galactic center and suggest that the central regions of our galaxy have experienced episodes of more violent activity in the past. Some astronomers speculate that these structures might be related to periodic feeding events when large gas clouds or even smaller galaxies fell into the central black hole, temporarily increasing its activity level and creating the energetic outflows that shape the observed filamentary structures. Understanding these features provides insights into the past activity of our galaxy's central engine and helps astronomers predict how the galactic center might evolve in the future as our galaxy continues to interact with its satellite companions and the broader cosmic environment. The study of our galaxy's central black hole also provides a unique window into fundamental physics, offering opportunities to test Einstein's general theory of relativity under conditions that cannot be replicated in laboratory experiments on Earth. The extreme gravitational fields near Sagittarius, a star, create effects such as gravitational time dilation, where time passes more slowly for objects deep within the black hole's gravitational well, and gravitational lensing, where the black hole's gravity bends the paths of light rays passing nearby. Future observations of stars orbiting close to the black hole may detect even more subtle relativistic effects, such as frame dragging caused by the black hole's rotation, providing increasingly stringent tests of our understanding of gravity and spacetime. These observations connect the largest structures in our galaxy to the most fundamental laws of physics, demonstrating how astronomical research contributes to our understanding of the universe at both cosmic and quantum scales. As you drift into peaceful sleep tonight, carried along by the gentle rhythm of cosmic contemplation, take comfort in the knowledge that even the most extreme and mysterious regions of our galaxy serve essential roles in maintaining the stable, nurturing environment that allows planets like Earth to exist and life to flourish. The supermassive black hole at our galaxy's heart, despite its awesome power and alien nature, acts as a cosmic anchor that has helped maintain the organized structure of the Milky Way for billions of years, ensuring that spiral arms continue their graceful dance and that stellar formation proceeds at the steady pace necessary for the gradual enrichment of the interstellar medium with heavy elements. From our safe vantage point, tens of thousands of light years away, we can observe and study this fascinating cosmic phenomenon while remaining comfortably within the galaxy's habitable zones, where the gravitational environment supports stable planetary orbits and the long-term conditions necessary for the emergence and evolution of complex chemistry, geology, and biology across the vast expanse of cosmic time. Allow your consciousness to drift now into the most beautiful and life-giving regions of our Milky Way galaxy, the magnificent stellar nurseries where new stars are born from vast clouds of cosmic dust and gas, creating celestial gardens that bloom with the brilliant colors of ionized hydrogen, oxygen, and other elements heated by the intense radiation of newborn stellar giants. These cosmic nurseries, scattered throughout the galaxy's spiral arms, like jeweled flowers in a cosmic meadow, represent the ongoing creative force of the universe, where gravity and nuclear fusion collaborate to transform cold, dark molecular clouds into blazing new suns that will shine for millions or billions of years. Tonight, as we explore these stellar birthplaces together, let your imagination soar through these cosmic gardens where the chemistry of stellar formation creates some of the most spectacular and photogenic objects in the galaxy, painting nebulae in shades of red, blue, and gold that capture the wonder and beauty of cosmic creation in progress. The most famous of these stellar nurseries lies within the constellation Orion, where the Great Nebula, officially designated M42, serves as a stellar maternity ward, visible to the naked eye as a fuzzy patch in Orion's sword. This glowing cloud of gas and dust spans approximately 24 light-years across and lies roughly 1,344 light-years from Earth, making it one of our closest and most accessible laboratories for studying the processes of star formation. Within the Orion Nebula, astronomers have identified more than 3,000 stars in various stages of formation, from tiny protostars just beginning to condense from the surrounding gas to massive young stars that have already ignited nuclear fusion in their cores and begun illuminating the surrounding nebula with their brilliant ultraviolet radiation. The nebula's characteristic reddish glow comes primarily from hydrogen atoms that absorb ultraviolet photons from nearby hot stars and re-emit the energy as visible red light, creating the cosmic equivalent of a neon sign that announces the presence of active star formation to observers across the galaxy. The process of star formation within these cosmic nurseries begins when regions of molecular cloud become dense enough for gravity to overcome the outward pressure of gas and radiation, causing the material to begin collapsing under its own gravitational attraction. These initial density fluctuations may be triggered by various mechanisms, including shock waves from nearby supernova explosions, compression caused by the galaxy's spiral density waves, or collisions between separate molecular clouds wandering through the interstellar medium. As the collapse proceeds, the cloud fragments into smaller clumps, each of which may eventually form an individual star or multiple star system. The collapsing material heats up due to gravitational compression, and when the core temperature reaches approximately 10 million degrees Celsius, nuclear fusion ignites and a new star begins its hydrogen-burning career. The entire process, from initial collapse to stellar ignition, typically requires several million years for Sun-like stars, though more massive stars can complete their formation in less than 1 million years. The Eagle Nebula, located about 7,000 light-years away in the constellation Serpens, provides another spectacular example of stellar nursery activity, featuring the famous Pillars of Creation, towering columns of gas and dust that have become iconic symbols of cosmic beauty and stellar birth. These pillars, which stretch several light-years in length, represent regions where dense material has resisted erosion by the intense radiation from nearby massive stars, creating elephant trunk-like structures that point toward the illuminating stellar sources. Within these pillars, astronomers have identified numerous stellar embryos called EGGs, evaporating gaseous globules, that represent stars in the earliest stages of formation, still cocooned within their natal dust clouds, but beginning to heat up as gravitational collapse proceeds. The interplay between stellar radiation and gravitational collapse in regions like the Eagle Nebula creates a complex dance of destruction and creation, where hot stellar winds and radiation gradually erode the surrounding material while simultaneously triggering the formation of new stars in compressed regions. The Horsehead Nebula, one of the most recognizable silhouettes in astronomy, demonstrates how stellar nurseries can create dramatic visual contrasts through the interaction of light and shadow on cosmic scales. This dark nebula, located approximately 1,500 light-years away in the constellation Orion, appears as a horsehead-shaped dark cloud silhouetted against the bright emission nebula AC 434. The dark appearance results from dense dust that blocks the light from more distant stars and nebulae, while the bright background glow comes from hydrogen gas ionized by the nearby hot star Alnitak. Within the Horsehead Nebula itself, astronomers have detected ongoing star formation activity, suggesting that this cosmic equine silhouette serves not only as a beautiful astronomical photograph, but also as an active stellar nursery, where new stars are condensing from the dense molecular material. The nebula's distinctive shape results from stellar winds and radiation pressure from nearby massive stars that have carved the surrounding material into its characteristic profile. These stellar nurseries exist throughout the Milky Way's spiral arms, where the higher density of gas and dust creates ideal conditions for gravitational collapse and star formation. The galaxy contains several thousand known star-forming regions, ranging from small, relatively isolated clouds that might produce only a few dozen stars, to massive star-forming complexes that can birth thousands of new stellar objects over periods of several million years. The largest and most active of these regions, such as the Carina Nebula and the Rosette Nebula, span hundreds of light years and contain enough raw material to form hundreds of thousands of stars, creating stellar associations and open clusters that will gradually disperse throughout the galaxy as they age, and the gravitational bonds between member stars weaken due to galactic tidal forces and encounters with molecular clouds. The chemical composition of stellar nurseries reflects the ongoing enrichment of the galaxy's interstellar medium through billions of years of stellar evolution, supernova explosions, and stellar wind mass loss. While the primary constituents remain hydrogen and helium, the primordial elements left over from the Big Bang, these clouds also contain trace amounts of heavier elements such as carbon, nitrogen, oxygen, silicon, and iron that were manufactured in the nuclear furnaces of previous stellar generations. These heavy elements play crucial roles in the star formation process, providing the dust grains that serve as condensation nuclei for molecular formation, and the cooling mechanisms that allow gas clouds to contract efficiently under gravitational attraction. The presence of these heavy elements also enables the formation of rocky planets around newly formed stars, creating the potential for terrestrial worlds like Earth, where complex chemistry and possibly life can develop over cosmic timescales. The energy feedback from massive newly formed stars creates complex dynamical processes within stellar nurseries that influence both the immediate environment and the broader galactic ecosystem. Young hot stars emit intense ultraviolet radiation that ionizes surrounding hydrogen gas, creating expanding bubbles of hot plasma that can trigger star formation in nearby regions while simultaneously dispersing the remaining natal cloud material. The most massive stars, with lifetimes of only a few million years, explode as supernovae before their parent stellar nurseries have fully dispersed, injecting tremendous amounts of energy and heavy elements into the surrounding interstellar medium. These supernova explosions can create expanding shock waves that compress nearby molecular clouds and trigger new episodes of star formation, creating a feedback cycle where stellar birth and death drive the ongoing evolution of galactic structure and chemical composition. Different types of stellar nurseries throughout the galaxy produce different populations of newly formed stars, reflecting variations in cloud mass, density, temperature, and chemical composition. Small, low-mass molecular clouds typically produce predominantly low-mass stars like red dwarfs and sun-like stars, while massive star-forming complexes can create the rare high-mass blue giants that burn brilliantly but briefly. The initial mass function, the distribution of stellar masses produced by a given star formation event, appears to be remarkably universal across different types of stellar nurseries, suggesting that the fundamental physics of gravitational collapse and fragmentation operates similarly regardless of the specific environmental conditions. However, the efficiency of star formation varies significantly between different regions, with some molecular clouds converting only a small fraction of their mass into stars, while others undergo more vigorous and complete episodes of stellar birth. The study of stellar nurseries provides crucial insights into the past, present, and future evolution of our galaxy, revealing how the Milky Way has transformed from a relatively simple collection of hydrogen and helium into the chemically complex, structurally organized spiral galaxy we observe today. Current star formation rates in our galaxy appear to be significantly lower than during earlier epochs, suggesting that the Milky Way has entered a more mature phase of its evolutionary history, where the available supply of star-forming material is gradually being depleted. However, interactions with satellite galaxies, infall of intergalactic gas, and recycling of material through stellar winds and supernovae continue to provide fresh fuel for ongoing star formation, ensuring that stellar nurseries will continue to bloom throughout the galaxy for billions of years into the future. As you drift toward peaceful sleep tonight, surrounded by the gentle rhythm of cosmic contemplation, imagine yourself floating slowly through one of these magnificent stellar gardens where new suns are being born in clouds of colorful gas and dust. The atoms in your body, carbon, oxygen, nitrogen, phosphorus, and countless others, were all forged in stellar nucleosynthesis within previous generations of stars that formed, lived, and died in similar cosmic nurseries billions of years ago. The calcium in your bones once flowed through stellar winds from dying red giant stars. The iron in your blood was manufactured in supernova explosions that briefly outshone entire galaxies. And the gold in any jewelry you might wear was likely created in the collision of neutron stars that sent ripples through the fabric of space-time itself. These stellar nurseries represent not just beautiful astronomical phenomena, but the fundamental creative processes that have manufactured every element necessary for planets, atmospheres, oceans, and life itself, connecting you intimately to the ongoing cosmic story of stellar birth, evolution, and the gradual enrichment of the universe with the building blocks of complexity. Let your mind now expand into the contemplation of one of the most profound mysteries of our cosmic existence, the invisible dark matter that surrounds and permeates our Milky Way galaxy like a vast, unseen ocean in which all visible matter floats like luminous islands in a cosmic archipelago. This enigmatic substance, which outweighs all the stars, planets, gas, and dust in our galaxy by a factor of at least 5 to 1, remains completely invisible to our telescopes, yet reveals its presence through the gravitational influence it exerts on everything we can see. Tonight, as we drift peacefully through this exploration of the galaxy's hidden architecture, imagine this dark matter not as something alien or frightening, but as the gentle cosmic scaffolding that has cradled our galaxy since its formation over 13 billion years ago, providing the gravitational foundation upon which spiral arms, stellar formation, and ultimately life itself have been able to emerge and flourish. Dark matter represents perhaps the most humbling reminder of how much about our universe remains mysterious and unknown, constituting approximately 85% of all matter in the cosmos, yet interacting so weakly with ordinary matter that it passes through planets, stars, and even our own bodies without leaving any detectable trace except for its gravitational signature. In the Milky Way, this invisible component forms what astronomers call a dark matter halo, a roughly spherical distribution that extends far beyond the visible boundaries of our galaxy, perhaps stretching out to distances of 300,000 light-years or more from the galactic center. This dark matter halo provides the gravitational foundation that determines the orbital velocities of stars throughout the galactic disk, creating the flat rotation curve that keeps stars in the outer regions of the galaxy moving nearly as fast as those closer to the center, a phenomenon that would be impossible if only the visible matter contributed to the galaxy's gravitational field. The discovery of dark matter emerged from careful observations of how stars and gas clouds move within galaxies, revealing motion patterns that could not be explained by the gravitational influence of visible matter alone. In the 1970s, astronomer Vera Rubin and her colleagues measured the rotation speeds of stars at various distances from the centers of spiral galaxies, expecting to find that stars farther from the center would orbit more slowly, just as outer planets in our solar system take longer to complete their orbits around the Sun. Instead, they discovered that stars in the outer regions of galaxies move much faster than predicted, maintaining nearly constant orbital velocities even at the very edges of galactic disks. This observation implied the presence of vast amounts of additional mass that could not be seen directly, but whose gravitational influence was essential for keeping these high-velocity stars gravitationally bound to their parent galaxies. Within our own Milky Way, the effects of dark matter become apparent when astronomers study the motions of satellite galaxies, globular clusters, and stellar streams in the galactic halo. These objects orbit the Milky Way at distances where very little visible matter exists, yet their orbital velocities indicate that they are moving through a substantial gravitational field created by invisible mass. Computer simulations of galaxy formation suggest that dark matter, halos like the ones surrounding our galaxy, formed first in the early universe, creating the gravitational wells into which ordinary matter later fell, condensed, and began forming the stars and gas structures that we observe today. Without this pre-existing dark matter framework, galaxies like the Milky Way could never have assembled the concentrated masses of ordinary matter necessary to trigger widespread star formation and create the complex spiral structures that characterize mature galactic systems. The nature and composition of dark matter remains one of the greatest unsolved puzzles in modern physics, with several competing theories attempting to explain what this mysterious substance might actually be. Leading candidates include exotic subatomic particles that were produced in the early universe, but interact only very weakly with ordinary matter and electromagnetic radiation, making them essentially invisible to conventional telescopes. These hypothetical particles, with names like WIMPs, weakly interacting massive particles, or axions, might occasionally interact with specially designed detectors deep underground, and particle physicists around the world are conducting sophisticated experiments to try to capture direct evidence of dark matter particles passing through Earth. Alternative theories suggest that dark matter might not consist of particles at all, but instead represent a modification to our understanding of gravity itself, requiring new physics beyond Einstein's general relativity to explain the observed galactic rotation curves and large-scale structure of the universe. The distribution of dark matter within the Milky Way appears to follow a roughly spherical pattern that astronomers describe using mathematical models such as the Navarro-Frank-White profile, which predicts how dark matter density varies with distance from the galactic center. According to these models, dark matter density is highest near the galactic center and decreases gradually toward the outer regions of the halo, creating a smooth, extended mass distribution that provides the gravitational framework for the galaxy's structure. However, recent observations have revealed that the actual distribution of dark matter in the Milky Way may be more complex than these simple models suggest, with possible asymmetries, substructures, and variations that reflect the galaxy's formation history and interactions with satellite galaxies over cosmic time. The Gaia space mission has mapped the positions and velocities of over 1 billion stars in our galaxy, providing unprecedented data that astronomers are using to infer the detailed shape and mass distribution of the Milky Way's dark matter halo. The invisible dark matter halo surrounding our galaxy plays a crucial role in determining the long-term stability and evolution of the Milky Way, influencing processes from the formation of spiral arms to the rate of star formation throughout the galactic disk. The gravitational influence of dark matter helps maintain the coherent rotation of the galactic disk over billions of years, preventing the differential rotation that would otherwise wind spiral arms so tightly that they would disappear completely. Dark matter also provides the gravitational anchor that keeps satellite galaxies like the Large and Small Magellanic Clouds in orbit around the Milky Way, creating the dynamic interactions that may trigger episodes of enhanced star formation and contribute to the ongoing evolution of galactic structure. Computer simulations suggest that without dark matter, galaxies would be much smaller, less structured, and less capable of sustaining the long-term stellar formation processes that have enriched the universe with heavy elements and created the conditions necessary for planetary systems and life. The search for dark matter extends beyond theoretical physics into direct observational efforts to map its distribution through gravitational effects on visible matter. Astronomers use techniques such as gravitational lensing, where the gravity of dark matter bends the light from more distant galaxies, creating distorted or multiple images that reveal the presence and distribution of invisible mass. Within the Milky Way, stellar streams, long trails of stars torn from disrupted satellite galaxies or globular clusters, serve as sensitive tracers of the gravitational field created by dark matter, allowing astronomers to map the shape and mass of the dark halo with increasing precision. These observations have revealed that dark matter halos are not perfectly smooth, but contain substructures and clumps that may represent the remnants of smaller dark matter halos that merged to form larger systems like our galaxy during the hierarchical process of cosmic structure formation. The cosmic significance of dark matter extends far beyond individual galaxies to encompass the large-scale structure of the entire universe, where dark matter serves as the gravitational scaffolding upon which clusters of galaxies, superclusters, and the cosmic web of filaments and voids have formed over billions of years of cosmic evolution. In the early universe, tiny fluctuations in dark matter density grew under gravitational attraction to create the first gravitational wells into which ordinary matter could fall and begin forming stars and galaxies. Without dark matter, the universe would be a much more uniform and less interesting place, lacking the hierarchical structure of galaxies, clusters, and superclusters that characterize the cosmos we observe today. The cosmic microwave background radiation, the afterglow of the Big Bang, shows the imprint of these early dark matter fluctuations, providing evidence that dark matter played a crucial role in cosmic evolution from the very earliest epochs of universal history. Recent advances in computational astrophysics have enabled scientists to create detailed computer simulations of how dark matter halos form and evolve over cosmic time, revealing the complex process by which smaller dark matter clumps merge and accrete to form the massive halos that surround galaxies like the Milky Way. These simulations predict that our galaxy's dark matter halo should contain numerous subhalos, smaller concentrations of dark matter that may represent the remnants of satellite galaxies that were disrupted by tidal forces during their infall toward the Milky Way. Some of these dark matter subhalos might be completely dark, containing no visible stars or gas, while others might host small satellite galaxies or globular clusters that we can observe today. The detection and characterization of these substructures provides important tests of dark matter theories and helps astronomers understand the formation history of our galactic home. As you drift into peaceful sleep tonight, carried along by the gentle rhythm of cosmic contemplation, take comfort in the knowledge that you exist within the protective embrace of this vast dark matter halo that has been nurturing and stabilizing our galaxy for over 13 billion years. This invisible cosmic ocean provides the gravitational environment that has allowed spiral arms to maintain their graceful patterns, enabled star formation to proceed at the steady pace necessary for chemical evolution, and created the long-term stability required for planetary systems like our solar system to survive and thrive over billions of years. The dark matter that surrounds us represents one of the universe's most profound mysteries, reminding us that the cosmos contains wonders and complexities that we are only beginning to understand. Yet it also demonstrates the fundamental interconnectedness of all cosmic structures, from the smallest subatomic particles to the largest galactic superclusters, all participating in the grand gravitational dance that has shaped the universe from its earliest moments to the present day. Allow your consciousness to drift now into the most profound contemplation of all, the vast temporal dimension of our Milky Way galaxy, where time unfolds across scales so immense that the entire history of human civilization represents less than a fleeting moment in the galaxy's ancient chronology. Our cosmic home has been slowly rotating through space for approximately 13.6 billion years, making it nearly as old as the universe itself, and bearing witness to cosmic events that dwarf human imagination. Tonight, as we journey together through these almost incomprehensible reaches of galactic time, Let your mind embrace the peaceful rhythm of cosmic eons, where stars are born, live out their nuclear careers, and die in cycles that repeat across billions of years like the slow breathing of the galaxy itself. This temporal perspective reveals that everything we consider permanent and unchanging, mountains, oceans, continents, and even species, exists within just the most recent few heartbeats of the galaxy's eternal temporal symphony. To truly appreciate the age of our galaxy, we must first understand that the Milky Way formed during the universe's youth, when the cosmos was less than 1 billion years old and very different from the structured, element-rich environment we observe today. In those ancient epochs, the universe contained almost no heavy elements. No carbon, no oxygen, no silicon, no iron. Only the primordial hydrogen and helium that emerged from the Big Bang's nuclear fusion processes. The first stars that formed in our galaxy were therefore composed almost entirely of these light elements, burning with different characteristics than modern stars, and ending their lives in spectacular supernova explosions that began the long process of chemical enrichment that continues today. These ancient stellar pioneers, known as Population 3 stars, were likely much more massive than typical modern stars, burning through their nuclear fuel in just a few million years before exploding and seeding the interstellar medium with the first traces of heavier elements that would eventually become incorporated into later generations of stellar formation. The formation of the Milky Way itself occurred through a complex process of hierarchical merging, where smaller proto-galactic fragments, each containing perhaps a few billion stars, gradually came together under gravitational attraction to form the larger, more organized structure we observe today. This assembly process took place over several billion years, with major merger events continuing until relatively recently in cosmic terms. Evidence for this formation history remains visible today in the form of stellar streams and tidal tails that mark the disrupted remnants of smaller satellite galaxies that fell into the Milky Way's gravitational embrace and were torn apart by tidal forces. The most dramatic of these ancient collisions may have been the merger with a galaxy that astronomers call Gaia Enceladus, which occurred roughly 8 to 10 billion years ago and contributed significantly to the formation of our galaxy's stellar halo and thick disk components. This collision was so massive that it temporarily disrupted star formation throughout much of the galaxy and left chemical signatures that can still be detected in the atmospheres of ancient stars today. The galactic clock ticks not in seconds or years, but in cosmic units of time that reflect the galaxy's fundamental rhythms and cycles. One of the most important of these temporal scales is the galactic year, the time required for our solar system to complete one orbit around the galactic center, which takes approximately 225 to 250 million Earth years. Since the formation of our solar system 4.6 billion years ago, we have completed roughly 20 of these galactic orbits, meaning that Earth has returned to approximately the same location in the galaxy only about 20 times since the planet first formed. During each of these grand orbital cycles, our solar system passes through different galactic environments, occasionally traversing the denser regions of spiral arms, where supernova rates are higher and cosmic ray flux increases, potentially influencing planetary atmospheres and even biological evolution through subtle changes in radiation levels and climate patterns. The chemical evolution of the galaxy represents another fundamental cosmic clock, ticking away as successive generations of stars gradually enrich the interstellar medium with heavy elements through stellar winds, supernova explosions, and other stellar death processes. This chemical clock shows a clear progression from the metal-poor stars of the galactic halo, which formed early in the galaxy's history when heavy elements were extremely rare, to the metal-rich stars of the galactic disk, which formed more recently from interstellar material that had already been enriched by billions of years of stellar evolution. Our own Sun, with its substantial content of elements heavier than hydrogen and helium, represents a relatively recent chapter in this chemical story, having formed from molecular cloud material that contained the nuclear ashes of countless previous stellar generations. The presence of these heavy elements in our solar system made possible the formation of rocky planets like Earth and the complex chemistry that underlies biological processes and ultimately the emergence of life itself. The star formation history of the Milky Way reveals another temporal rhythm, with episodes of enhanced stellar birth alternating with quieter periods when star formation rates decreased due to various galactic processes. During the galaxy's early epochs, star formation proceeded at much higher rates than we observe today, creating the massive stellar populations that we see in globular clusters and the galactic bulge. These ancient star-forming episodes consumed vast quantities of available gas and dust, while the resulting supernovae and stellar winds heated the interstellar medium and temporarily suppressed further star formation in affected regions. Over time, the overall star formation rate in the galaxy has gradually declined as the available supply of star-forming material has been depleted through stellar consumption, and as feedback processes from massive stars have become more effective at regulating the collapse of molecular clouds. However, the galaxy continues to form new stars today, though at a much more sedate pace than during its more vigorous youth. The orbital periods of different stellar populations provide additional insights into the galaxy's temporal evolution, with kinematic studies revealing how the galaxy's gravitational potential and mass distribution have changed over cosmic time. The oldest stars in the galactic halo show highly elliptical, randomly oriented orbits that reflect the chaotic conditions present during the galaxy's formation, when multiple proto-galactic fragments were still in the process of merging and settling into organized rotation. In contrast, younger disk stars, like our Sun, follow more circular, well-ordered orbits that lie close to the galactic plane, reflecting the gradual settling and organization that occurred as the galaxy matured and developed its current spiral structure. These kinematic patterns preserve fossil evidence of the galaxy's dynamical evolution, allowing astronomers to reconstruct the timeline of galactic assembly and identify the epochs when major structural components formed. The life cycle of individual stars within the galaxy operates on timescales that vary dramatically depending on stellar mass, creating a complex temporal tapestry where different types of stars age at vastly different rates. The most massive stars, with masses exceeding 20 times that of our Sun, complete their entire evolution from birth to supernova explosion in less than 10 million years. A time span so brief that these stellar giants live and die many times over during a single galactic rotation. At the opposite extreme, the smallest red dwarf stars burn their nuclear fuel so efficiently that they can continue shining steadily for hundreds of billions of years, far longer than the current age of the universe. Our own Sun, representing a middle ground between these extremes, will burn hydrogen in its core for approximately 10 billion years total, meaning it has already completed nearly half of its main sequence lifetime and will continue shining for another 5 billion years before evolving into a red giant and eventually a white dwarf star. The supernova explosions that mark the deaths of massive stars provide another important galactic timekeeper, occurring throughout the Milky Way at an average rate of roughly one explosion every 30 to 50 years. These stellar detonations not only enrich the interstellar medium with heavy elements, but also create expanding shock waves that can trigger the formation of new stars in nearby molecular clouds, creating a feedback cycle that helps regulate the ongoing evolution of galactic structure. The supernova rate has varied over the galaxy's history, with higher rates during epochs of more vigorous star formation and lower rates during the current, more quiescent phase of galactic evolution. Some astronomers have suggested that variations in supernova rates might correlate with mass extinction events in Earth's fossil record, though such connections remain highly speculative and controversial. The gradual orbital evolution of our solar system provides another window into deep galactic time. As gravitational interactions with passing stars, molecular clouds, and spiral density waves slowly modify our orbital parameters over periods of hundreds of millions of years. These perturbations can alter the eccentricity of our galactic orbit, change our maximum distance above or below the galactic plane, and influence our exposure to cosmic radiation from the galactic center and nearby massive stars. Computer simulations suggest that our solar system's orbital characteristics have remained relatively stable over its 4.6 billion year history, contributing to the long-term climate stability that allowed life to emerge and evolve on Earth. However, future encounters with massive molecular clouds or the ongoing merger with the Andromeda Galaxy, scheduled to begin in approximately 4.5 billion years, may eventually alter our galactic orbital parameters and change the cosmic environment that Earth experiences. As you drift toward peaceful sleep tonight, carried by the gentle rhythm of cosmic time itself, imagine yourself as part of this vast temporal symphony that has been playing since shortly after the universe began. The atoms in your body, forged in stellar cores billions of years ago, scattered through space by ancient supernovae, and eventually incorporated into the molecular clouds from which our solar system formed, carry within them the chemical memory of deep galactic time. Your existence represents a remarkable confluence of cosmic circumstances that required the galaxy to evolve for over 9 billion years before conditions became suitable for the formation of metal-rich stars like our Sun and rocky planets like Earth. The galactic clock continues to tick in its measured cosmic rhythm, marking time not in human moments, but in stellar generations, spiral arm passages, and the slow chemical enrichment that gradually transforms galaxies from simple collections of primordial gas into complex ecosystems capable of nurturing the emergence of planetary systems, organic chemistry, and ultimately the self-aware consciousness that allows you to contemplate your place within this magnificent temporal tapestry of cosmic evolution. Let your mind now expand to embrace the most profound perspective of all, our Milky Way's place within the vast cosmic community of galaxies that populate the universe, revealing that our galactic home, magnificent as it is, represents just one member of an even grander cosmic family, stretching across billions of light years of space and time. Tonight, as we complete our gentle journey through the scale and wonder of our galaxy, we discover that the Milky Way exists not in cosmic isolation, but as part of the local group, a gravitationally bound collection of more than 80 galaxies that dance together through the expanding universe, each following its own orbital path within this cosmic neighborhood that spans approximately 10 million light years from edge to edge. This revelation places our galactic home within an even larger hierarchy of cosmic structure, where groups of galaxies cluster together, and those clusters form superclusters, creating a cosmic web of matter and energy that extends to the very edge of the observable universe and beyond. The local group represents our immediate galactic neighborhood, dominated by three massive spiral galaxies: our own Milky Way, the slightly larger Andromeda Galaxy, and the slightly smaller Triangulum Galaxy Andromeda Galaxy, and the smaller, but still substantial Triangulum Galaxy, also known as M33. These three cosmic giants account for the vast majority of the local group's total mass and stellar population, while dozens of smaller dwarf galaxies orbit around them like cosmic satellites, including the famous large and small Magellanic Clouds that are visible from Earth's southern hemisphere as fuzzy patches of light in the night sky. The gravitational influence of these three major galaxies has shaped the structure and evolution of the entire local group over billions of years, determining the orbital paths of smaller galaxies and influencing the rate of star formation throughout this cosmic community. The distances involved are staggering even by galactic standards. The Andromeda Galaxy lies approximately 2.5 million light-years away, meaning that the light we see from it tonight left that galaxy when our earliest human ancestors were just beginning to walk upright on the African savanna. For decades, astronomers have predicted that our Milky Way and the Andromeda Galaxy are on a collision course, racing toward each other at approximately 250,000 miles per hour in what would be one of the most spectacular cosmic events imaginable. This anticipated galactic merger, originally predicted to occur in about 4.5 billion years, captured public imagination and became a fixture in astronomy textbooks and documentaries as an example of cosmic evolution on the grandest scales. The collision would unfold over billions of years, with the two spiral galaxies first passing by each other, their mutual gravitational influence distorting stellar orbits and triggering massive episodes of star formation as gas clouds collide and compress. Eventually, after several billion years of gravitational interaction, the two galaxies would merge to form a single, massive elliptical galaxy that astronomers have playfully dubbed Milkomeda, a cosmic metropolis containing the combined stellar populations of both original galaxies arranged in new orbital configurations. However, recent research has revealed that the future of our galactic neighborhood may be far more uncertain than previously thought, with new calculations suggesting only about a 50% probability that the Milky Way and Andromeda will actually merge within the next 10 billion years. This dramatic revision in our understanding of galactic destiny emerged from more sophisticated computer simulations that account for the gravitational influences of other local group members, particularly the Triangulum Galaxy and the Large Magellanic Cloud, whose orbital motions create complex three-body and four-body gravitational interactions that significantly affect the predicted trajectories of the two major spiral galaxies. The Large Magellanic Cloud, currently in the process of being disrupted by the Milky Way's tidal forces, may actually deflect our galaxy's path away from Andromeda, while the Triangulum galaxy's gravitational influence appears to increase the probability of collision. These competing effects, combined with uncertainties in measuring the precise positions, velocities, and masses of all involved galaxies, have transformed the predicted cosmic collision from an inevitable certainty into a statistical coin flip. The profound uncertainty surrounding our galaxy's future reflects the fundamental challenges of predicting cosmic evolution over such vast temporal scales, where small changes in initial conditions can lead to dramatically different outcomes over billions of years. The positions and velocities of galaxies can be measured with extraordinary precision using modern space telescopes like Hubble and Gaia. Yet the uncertainties that remain, measuring galactic motion to within a few kilometers per second across millions of light years, become magnified enormously when projected billions of years into the future. Additionally, the complex gravitational dance between multiple massive objects creates what mathematicians call a chaotic system, where tiny perturbations can accumulate over time to produce wildly divergent evolutionary pathways. This cosmic uncertainty principle reminds us that while we can understand the fundamental physics governing galactic interactions, the specific details of our cosmic future remain tantalizingly beyond our predictive reach. Regardless of whether the Milky Way and Andromeda eventually merge or simply pass by each other in a cosmic near miss, both scenarios would profoundly transform the local group structure and evolution over cosmic time. A successful merger would create one of the most massive galaxies in our local region of the universe, potentially triggering enhanced star formation rates and creating new stellar populations with different chemical compositions and orbital characteristics. Alternatively, a close encounter without merger might strip gas and stars from both galaxies through tidal interactions, creating stellar streams and disrupting the organized spiral structure that characterizes both systems today. Either outcome would reshape the gravitational landscape of the local group, affecting the orbital evolution of smaller satellite galaxies and potentially altering the cosmic environment that future civilizations might encounter billions of years from now. The local group itself exists within an even grander cosmic structure known as the Virgo supercluster, a vast collection of galaxy groups and clusters that spans roughly 110 million light-years and contains more than 1,300 known galaxies. Our local group occupies a relatively quiet region on the outskirts of this supercluster, moving slowly through the cosmic web under the gravitational influence of the massive Virgo cluster, located approximately 50 million light-years away. This larger cosmic context reveals that galactic interactions and mergers represent common phenomena throughout the universe, with galaxy clusters serving as cosmic mixing bowls, where gravitational encounters, tidal stripping, and galactic cannibalism continuously reshape the stellar populations and morphologies of their member galaxies. The study of other galaxy groups and clusters provides important insights into the possible futures that await our own local group, showing how cosmic evolution proceeds on the largest observable scales. The cosmic web structure that organizes matter on the largest scales consists of vast filaments of dark matter and galaxies separated by enormous voids, containing very little visible matter. The local group currently resides within one of these cosmic filaments, slowly flowing toward the gravitational attractor known as the Great Attractor, a massive concentration of galaxy clusters located roughly 150 million light-years away in the direction of the constellation Centaurus. This cosmic current carries our entire galactic neighborhood through space at approximately 600 kilometers per second, a motion so vast that it dwarfs the orbital velocities within individual galaxies, yet proceeds so smoothly that it can only be detected through careful measurements of the cosmic microwave background radiation and the positions of distant galaxy clusters. Understanding these large-scale motions provides crucial context for interpreting the local dynamics of the local group and predicting how our cosmic neighborhood will evolve as it participates in the ongoing expansion and evolution of the universe itself. The discovery of thousands of exoplanets orbiting stars throughout the Milky Way has raised profound questions about the potential for life elsewhere in our galaxy and throughout the broader cosmic community. If Earth-like planets are common around Sun-like stars, then our galaxy alone might harbor millions or billions of worlds where conditions suitable for life could develop over cosmic timescales. The local group, with its hundreds of billions of stars distributed across dozens of galaxies, represents an even richer environment for the potential emergence of life and intelligence. Future galactic evolution, whether through merger with Andromeda or continued separate existence, will create new stellar environments and planetary systems that might provide homes for forms of life and consciousness that we cannot yet imagine. This cosmic perspective transforms the question of humanity's place in the universe from a local concern to a galactic and intergalactic consideration, suggesting that we might be part of a vast community of conscious beings distributed throughout the cosmic web. As you drift into the most peaceful sleep tonight, carried along by the gentle rhythm of cosmic contemplation, let your consciousness expand to embrace this magnificent perspective on our place within the vast hierarchy of cosmic structure. You exist not just on a planet orbiting a star within a galaxy, but as part of a cosmic community that extends from the local group to superclusters to the cosmic web itself, all participating in the ongoing expansion and evolution of the universe since the Big Bang nearly 14 billion years ago. The atoms that compose your body were forged in stellar cores throughout this cosmic community, scattered by supernova explosions across galactic distances, and eventually gathered together in the molecular cloud from which our solar system formed. You are literally made of star stuff from throughout the local group, carrying within your very being the chemical signatures of cosmic evolution on the grandest scales. The future remains beautifully uncertain, with possibilities ranging from galactic merger to cosmic near miss. But in either case, the cosmic community that surrounds us will continue its eternal dance through space and time, creating new opportunities for wonder, beauty, and perhaps even consciousness to emerge from the fundamental forces that govern the universe itself. Before you drift completely into dreams of cosmic wonder, remember to subscribe to the Sleepy Cosmoz for more peaceful journeys through the mysteries of the universe that will carry you gently toward restful sleep. Hit that notification bell to never miss our cosmic explorations. Give this video a like if our journey through the magnificent scale of the Milky Way has filled you with wonder, and let us know in the comments what cosmic mysteries you'd like us to explore next in our ongoing quest to understand our place within the infinite beauty of the cosmos.